think. See, okay, you are listening to me, right? Okay. So I think we will now start this webinar. So this webinar aims at showcasing many of the developments that we have done throughout the infield project. And today we are going to be talking about the application of AI to renewable energy integration and electrical mobility. We will have three presentations. Each presentation will be around 15 minutes, and then we will have 5 minutes for a short Q&A, okay? Feel free to use the Q&A section for questions, and they will be addressed in those 5 minutes. So we will now start with the first presentation, entitled Explaining the Optimization of Dynamic Tariffs for Electrical Vehicles, that Tiago Bessa will present.
Let me just share the screen. You can see my screen, right?
Yes.
Okay.
Okay.
Okay. First of all, good afternoon for everyone. Thank you for joining this webinar. Today I'm going to be talking about the subject that I have been working on since my master's dissertation. As Francisco told you, it's entitled Explaining the Optimization of Dynamic Tariffs for Electric Vehicles. So I think we should start by dividing the title of this presentation into several parts and start by the electric vehicles. That we all know that electric mobility has been rising, has been increasing, but we do still face some limitations like driving range anxiety, the availability of charging infrastructure, and the complexity that comes with managing that charging demand. To tackle this last issue, we end up developing several charging control strategies, direct or indirect, and among these latter, dynamic pricing. Dynamic pricing is basically a form of demand response where we use price signals to adjust charging demand according to conditions from the grid. However, when we are trying to develop this kind of strategies, we develop optimization models that are really challenging to understand, meaning that we cannot establish a relationship between the output, between the input and the output or solution of the model. This is called the black box problem. So the project that I have been working on tries to tackle this issue by explaining this optimization. Therefore, we aim at improving trust so that EV users or many other stakeholders can use this type of technique that we recognize as beneficial, not only for them, but also for the grid. So very shortly, these were the steps that I took during my master's dissertation and during the following work that took place. Basically, I spoke about an optimization model, so we have to basically have it ready, and that was the case. So my job was only to perform the long-term execution of this model and then generate the data frame so that we could do an initial analysis of this data set. Then we had two main stages. The first one, the machine learning pipeline, where we used several tree-based models so that we could assess the trade-off that these models have regarding, for instance, their capability of approximating the behavior of the tariffs and regarding also their interpretability. Then we have perhaps the most interesting part, at least to me, that was to see if large language models were capable of doing this same task, meaning approximate the behavior of the tariffs, but doing that in an interpretable and explainable way. So starting by the first stage, I think it's important first that we simply talk a little bit about the optimization model. This was not developed by me, it was developed by my supervisors, and it is essentially a charging station cost minimization problem. It's a stochastic optimization because it handles uncertainty regarding solar generation, carbon intensity from the grid, and load. Of course, it also handles price elasticity of demand, and the decision variable is tariffs. The long-term execution of this optimization model provided a data set with almost 50,000 instances, 20 features, and one target variable that was, of course, the EV charging tariffs. So this is an initial analysis that I had to do. Basically, what you see here are the target variable tariffs and 3 other features, such as market prices, the solar generation, and charging demand. These initial charts show a big it shows that tariffs and market prices follow the same time structure, temporal structure, and they both have low values when we have an increase in solar generation. Of course, due to the way that the optimization was modeled, tariffs are much more affected by the charging demand, because even when they have low values due to the increased solar generation, when we have a peak in charging demand, those tariffs also increase. So, talking about the machine learning pipeline, we wanted to develop something that was capable of running multiple tree-based models. And the goal here was to see if they could have a good predictive performance, be faithful to the tariff definition, basically, and if they were how interpretable, and assess how interpretable they were, so that we could perform a trade-off. The steps in the gray boxes that you see here below are basically the common steps of machine learning pipeline, and I'm not going to be expanding on them because it's a very well-known subject, but it's worth noting that due to the fact that we were not interested in having the best performance-wise model, we did not put in much effort in pre-processing data. We only removed highly correlated features. We used multiple models, the simplest one being the decision tree regressor. It's a simple decision tree that enables the direct extraction of the decision-making process. Then we also used the M5 prime that uses linear regressions at the leaves, and then the assembled models, the random forest regressor, an example of a pegging algorithm, and the latter 3 that are boosting models. However, in order to basically enact that trade-off, we had to come up with a way to measure interpretability. So we inspired ourselves in previous works, and basically we defined the total mental operations in a decision tree as defined through the number of splits, the number of assignments, and the number of linear operations in the tree, if there are any. These were the results that we had. Basically, the bar charts that we see on the top left is performance-wise, the prediction error. And the results here are somewhat surprising, but there are also some things to be expected. For instance, linear regression, the first bar, of course, could not capture the non-linear patterns of the data set, so it had the worst results. It's basically serves as a baseline. However, the best performing model in terms of prediction accuracy was XGBoost. It's a well-known, very powerful tree-based model. So that was to be expected. What was a surprise was that the decision tree, theoretically the simplest algorithm, also had a pretty similar result, meaning that now we could have a model that could approximate the results of the optimization, was faithful to the optimization, and it was also interpretable. You can directly extract the decision-making process. However, XGBoost is not directly interpretable, but it's explainable. You can use strategies like extract the fiction importance of the model and see which features are directly impacting the model the most. In this case, it was the tariffs-like feature and some others like our self-elasticity, load, and metrics related to the solar generation that acted as tiebreakers. If we see the chart on the right, we see the trade-off that I've been speaking since the beginning. This is the trade-off between interpretability and prediction performance of a single tree. And what it shows basically is that in our case, the decision tree was the best solution since it combined high predictive performance with high interpretability. Okay. Now I think we've come to the most interesting point of the presentation because it uses an emergent technology that are the large language models, which everyone nowadays is using. So the goal here was to check if large language models were capable of acting as an optimization surrogate in an interpretable and explainable way. So the initial steps are the same. We have an optimization model, we make the long-term execution of this optimization, and then we generate a data frame. This data frame then is fed to an LLM. This LLM framework is basically composed by two large language models. One that is responsible for generating the rule set, and another one that is responsible to provide suggestions or recommendations on how to improve this rule set. However, we have, and this is an iterative cycle, so the recommendations should improve the rule set until we reach a certain goal, like the maximum number of iterations or a minimum error, prediction error. So some notes regarding this framework. Of course, that we cannot pass a whole data set in a single prompt. So what we do is we implement a sliding window that varies between iterations so that the LLM ends up actually seeing the whole data set. For this case, we use the same large language model for the rule generator and for the feedback generator, the DeepSeek R1 Distill Quen 32 billion. This was all implemented in Python, and I think that's the main topics. So one thing that is really important when we are working with large language models is to make a good prompt. So we try to be as clear as possible and give as much information as we can give them without confusing the large language model. So what we did was, for the case of the LLM that was responsible for generating the rule set, we provided an expertise, context, the iteration number, the target variable, the feature descriptions, the data, which is the current training set, and a data set summary, basically a statistical summary, and prior knowledge, that is the rules from the previous iterations, the best rules so far, and the feedback that the other LLM basically gave. Then we also follow the best practice regarding prompt formatting. We introduce few short examples and a chain of thought. The LLM feedback prompt is basically the same, but here I'd like to highlight one point, that is, here we had something that I call the history table. That basically, it's a table where we basically describe the changes that happened between iterations and the effect that they had on the prediction error. This will enable the LLM feedback to know which recommendations worked and what did not work, basically, so that he can direct the next suggestions in the direction of the steepest descent of the error. This is the results that this framework provided. If we look first for, here we have two different charts. The first, the May over different iterations and over the different iterations, and the chart below that is basically the best error so far until a given iteration. What we see here is clear that the framework is working, meaning that the error is actually decreasing over time. However, we do have some things here that we have to note. If you look to the first chart, you see that there is a lot of noise. This is basically some attempts that the LLM took and they did not result. So the framework discards those suggestions and he tries again until the error actually decreases. Here we compare it, the yellow line and the red line. We are comparing the rule sets with the ones with the linear regression and the Shish-Boost model, and we actually surpassed the linear regression and achieved a pretty close result to Shish-Boost. As I said previously, we wanted to make this in a way that was both explainable and interpretable. In the interpretable, first, if we speak about interpretability, the LLM is prompted to return a Python function that basically is a decision tree. It's a if-else tree-based model, basically. Or furthermore, It also provides a justification in natural language. It talks about the nature of the dataset, the patterns that it identifies, and the feedback that he was recommended to implement. Of course, it also outputs the changes made string, that is the sentence that is going to be introduced in the history table that I talked about earlier. Then, in order to make this accessible to any user, technical or non-technical, what we do is we basically extract the decision tree that the framework generated, and then we feed it to another LLM so that it can transform it in natural language. And basically, I'm not going to read all of this that is here, but I think that the last paragraph is the most important thing. The big takeaway that says that yesterday's price set the stage, and steady forecasts mean gentle prices, while volatility and low sensitivity quickly push them higher. This ends up providing a more accessible explanation than reading a Python function. To conclude, we have here two main stages. The first one, that was using machine learning, provided the best surrogate, provided the following results. First, the best surrogate was indeed XGBoost performance-wise. But for us, for the purpose of this work, which was to make the EV charging tariffs interpretable, the decision tree offered a practical trade-off, because although it have a slightly lower performance, it enables the direct extraction of the decision-making process. Regarding the LLM, we saw that the rule-generated framework was capable of building and refining each iteration interpretable rule sets for EV charging tariffs, and that the explainer was able to translate this model to non-technical users. Some limitations. I'd like to focus here on the LLMs, because the LLMs suffer from prompt sensitivity, hallucination, and high computational resource requirements. And they face high computational resource requirements. Running this kind of framework is a heavy task, and the resources are expensive to do so. And of course, another thing that you might be wondering, we here had different results per simulation, because it is really hard to ensure determinism in the LLM output, which ends up also being an issue that we have to face. Future work. Regarding the natural language explainer, we could also add the feedback cycle and use features like SHAP to increase the quality of the information that we provide the LLM. And the LLM rule generated, I'd like to be able to tell them an explicit trade-off, meaning you should prioritize interpretability by 80%, something like that. And also that is something that it's quite being used today. Explored, we'd like to do this in an agent pipeline framework. So that was it. Thank you. I'm hoping to any questions that you might have. Thank you. Let's lift it up.
Yeah, you might have a question already in the chat.
This work is not published yet. It's a work in progress. There is an abstract submitted to EAM, but it's not published yet. It's published in my master's dissertation, to be fair. I don't know if there are any other questions.
Have you seen that one?
No. Sorry. What is the payoff return of this methodology? For example, in Portuguese electrical systems under condition of production mix and consumption. What is the pay? Under the these methodologies, I don't know if I understand correctly the question, but this methodology was the goal here is more related to how the goal is more related to explaining an optimization tool, because it's to solve the black box problem. It's more of more useful. It's It's something that would be useful for many stakeholders like EV users, but mainly to charging station operators and regulators or policymakers, that they will be able to understand what really affects the definition of these tariffs and adjust according to their needs.
Okay.
Thanks. I don't know. I think there are no more questions.
Okay.
Thank you.
Okay, so maybe we can go for the second presentation by Carol. Okay.
Can you see the slides? So hello, my name is Carla Gonçalves. I am also a researcher in the Center for Power and Energy Systems at INESC TEC. And this presentation is about privacy preserving and trustworthy federated learning with a new family of networks called Kolmogorov Arnold networks. First, I would like to emphasize that this work was developed within the second exchange scheme. So EnField project allowed us to propose some topics for this exchange scheme, and then we could select some candidates if there were interesting candidates for our topics. And in my case, Lucas Cipel from Mine Paris was the selected candidate, and he had the opportunity to work with me here in Porto at INESC TEC during a period of 5 months. So the work that I will show you next was developed by him during this 5-month period. So starting with the motivation, why do we need this privacy preserving federated learning? First, renewable generation is variable, and we need accurate forecasting models to support decision making. And we see that forecasting models are hitting a ceiling without diverse data. So we can still do better models, but we see that the tendency is to fit the models with better and more diverse data. And data should not be a problem because we have wind farms, solar plants, buildings. They all are equipped with sensors and they continuously generate and collect data. So the data exists, but the problem is that these wind farms, solar plants, buildings, they are owned by different data owners, and usually they are unwilling to share their data, even because of business competitive factors or personal data protection when we are talking about low data, for example, in our houses. So as a solution, we can propose privacy preserving techniques to estimate the models without really having data sharing. But this is not enough because we see that the European Union Artificial Intelligence Act asks for trustworthy models. So we need to ensure privacy and also trustworthiness. And this sometimes is difficult because when we introduce privacy, we encrypt the data, we encrypt connections, so we encrypt everything. So if we encrypt, how can we have a trustworthy model? How can we understand who was responsible for a bad forecast, etc. And in the beginning of end of 2024, we saw this opportunity in Kolmogorov Arnold networks. So it was a new family of networks. It appeared in 2024. And it has some properties that are interesting for privacy preserving federated learning because they use spline functions. So they transform the data with spline functions, and then they just had these spline functions. And this is interesting because it is easy to split operations across the partners, the data owners. The splines are naturally interpretable. The splines can be approximated with symbolic expressions. And with that, we at the end, we have a formula for our forecast. We know exactly how the forecast is being produced. And all these properties are privacy friendly by design because we just have a sum of functions. It's good for secret sharing, homomorphic encryption, etc. So first I talked about these Kolmogorov Arnold networks, but what is it? So here we can see an example. In this case, we have two input variables, one output variable, and what happens in the middle is that each feature, each variable, is transformed with functions. These functions are learnable functions, and then the neurons just sum these functions. So we learn the functions, and then we just sum. We learn new functions, and we just sum, etc. And in terms of multi-layer perceptron, so it's similar, but it's different because in multi-layer perceptron, we learn the weights, the x1 times 5, for example, x2 times 2, and then we have, and then we pass by an activation function that is fixed from the beginning. Usually it is a ReLU or a sigmoid. And this is the main difference between both. So here we learn the weights and the functions are fixed. Here we learn the functions and then we just sum them. How do we learn the CAN? So first we need to fix the spline family that we want to use. Usually we use the B-splines, but it could be polynomial splines. So polynomial splines is basically data power 2, data power 3, etc. And then after fitting these splines, we also need to learn coefficients to multiply these splines. And this is done as we do in multi-layer perceptron with backpropagation. We start with a random initialization of the weights, and then we update them. And we also update the size of our splines, the order of our splines. So this is, in a very brief way, what CANs are. Now, in terms of interpretability, why do people say they are interpretable? First, so this is a complex thing. So we have many connections, edges. So we can do some pruning to start. One of the techniques to prune is we compute the max norm of node input and output. So the absolute value of the input in a certain layer and the output. And if the maximum of these two values is below a certain threshold, we prune this edge. So we can simplify a lot the network. Then we can do a symbolic representation. So each of these spline functions can then be approximated with a set of symbolic functions. For example, here the approximation could be x, exponential of x, here minus x, maybe x cube, and then at the end this CAN represents this model. So it's this expression that is being learned by this CAN architecture. So the y is exponential minus x1 plus x2 power 3. So this is interpretable. Well, it depends. Sometimes it's really hard to look to this expression and understand exactly if I change x1, what will happen in the y. But since we have this expression, we can add the interpretability by using the partial derivatives of the response with respect to each input. And with that, we know the impact that each feature has in the final model output. So this is one of the nice properties of the CANs. The other one is verifiability in terms of verify if the output makes sense or not, because we know that if we are working with renewable energy, the output should be something between 0 and installed capacity. So if it is outside these limits, it does not make real sense. And with this expression, we know that if the variables are limited, so if we are using wind speed, we know that is usually between 0, and we can set a maximum, a limit, a historical maximum, for example, and we can see the behavior of this expression and see if there are regions that don't make sense. So this allows for bounds for prediction and also detect anomalies when we do the forecast. Now, they can seem to have really nice properties, but what about data privacy? That is our concern. Here, they are not that good because the learn functions, they are interpretable, which means that an attacker, for example, if this is a data owner, this is another one, then this data owner has is the first one. Data owner 2 will have this. Data owner 1 has this one. So data owner 2 will receive a linear transformation of the feature X1. So if it is about power measurements, then owner 2 will be able to recover sensible data. So they are not that robust for data privacy, so we need to do something about that. And this was what Lucas proposed and developed during his work. So basically, we have 3 data owners here represented with different colors. Each data owner has his own features, and what we first proposed was introduce privacy only using the architecture. So we don't need homomorphic encryption or other kind of robust encryption. So our proposal was each of these data owners train a local CAN that transforms and projects data into lower dimensional space. And with that, we are protecting the sensible data. So we based ourselves in this paper from 2022. And after doing these local CANs, we can connect the local CANs to a global CAN that receives as input the local embeddings. And then at the end, the forecasts are aggregated by the corresponding owner to ensure privacy, because if the blue does the final sum for the green, then he has a forecast. So it's not supposed to do that. So here we have privacy by design. The main problem can be that we are, in the beginning, we are forcing pruning of the CAN, because we are not allowing in the first layers of the network that edges exist between these blocks. So this is the first proposal. And we can also have interpretability after these nodes here. So we can understand how the information coming from the orange influenced the forecast for the blue, etc. Now, there is also the possibility of having encryption with other means for that. And Lucas Tippel was doing the PhD when he came to INESC TEC, and before he worked with secret sharing for multivariate regression trees, and we decided to apply it here as well. And the idea is, again, 3 data owners. They all want to do forecasts. They all have input features. We have here a function, and the idea is that, let's say I have the x, I pass through the learn function, and the value is 10. So instead of sending 10, the value 10 to all the others, we will split these 10 in secrets that can be 5, 3, 2, for example, and then we send the 5 just to blue, the 3 to orange, the 2 to the green, and then they have to communicate to recover the sum, just knowing the shares. So here the problem is the computational complexity, because to compute the first layer of the CAN, they need to communicate with each other, between them, all these secrets, and then sum them. So there is a lot of communications here, but then they can proceed with a normal CAN after that, because the problem is the first layer of the CAN, and then at the end it's the same. So each data owner recovers the own forecast. So here we are not forcing this initial pruning on the bottom of the network, but we have this communication burden. Now, in terms of case study, we use data from JEFCON. This is open data, that's why we used it. So the period is 23 months, hourly data. The input features we used is the 6 most recent power values, and also numerical weather predictions for wind speed. We have the U and V coordinates. We trained our model with 12 months, and then we did the slide of we predict the next 1 month, then we slide, etc. In terms of evaluation metrics, we used the root mean square error and mean absolute error. And the horizon, we did can for 1 hour ahead, 2 or 3, up to 9 hours ahead. And yeah, and we experimented the models just using the power measurement, so a pure autoregressive model, and also use the most recent power measurements plus the numerical weather prediction. And here are the results. So I will try to just do a brief summary. So here on the left panel, we see the results using only the lags, the power measurements. And on the right panel, we see power measurements plus numerical weather predictions. First line is when we do 1 hour ahead. Second is 3 hours ahead. And the last one is 9 hours ahead. And then we also benchmarked against some known models like linear lasso regression, B-spline lasso, gradient boosting regression, multi-layer perceptron also, and then we have all the CAN variations. So initial CAN pruned, symbolic CAN, and the same for the fusion CAN. And the main conclusion is that CANs are competitive. So, and I would like to emphasize that our goal here is not having better forecasts. The idea is to be similar to multi-layer perceptron gradient boosting regressor because they are non-linear models. So this is our goal, to be competitive, not necessarily better, but with the advantage that we can ensure privacy and have interpretability and some verifiability for the output of the model. Of course, during the experimental part, while implementing this, we saw some training instability. It's normal with neural networks, and this happened because we needed to do hypertuning. When we tried default parameters, we had a lot of instability. So it's really important to do good fine-tuning, and we did it with Bayesian optimization. The pruning sensitivity is also very important because if we are too aggressive, then we will prune all the edges. If we don't, we will lose some interpretability because at the end the expressions are huge. And there are also some symbolic singularities sometimes because if it learns, for example, that the function is 1 over x, and it learned in a training set that didn't have the zeros, when a zero happened in the test set, then we have a problem because of the 1 over 0. Now, in terms of feature importance, because we also want to have this kind of analysis, here is an example when we do the 4 hours ahead, with these combined 6 most recent power measurements and numerical weather predictions. In the black values means that, for example, farm 1, the features did not contribute to farm 10, etc. So in general, what we see is that farm 4, for example, does not use data from farm 1, farm 7 has high contribution to farms 1, so farm 7 has high contributions to farm 1, we can see here, so the lighter colors, 5 and 6. So we see here that one of the variables from farm 7 is contributing a lot to farm 5 and 6. And overall, most farms rely only on a small subset of features. In terms of the prediction bounds, so we have the expressions, they were a bit large expressions, and then we wanted to see if these expressions had some problems in terms of bounds. So if it could happen that we had extremely high values that did not make sense. So to do that, we need to generate the features between 0 and the maximum that they can take. If we do this randomly, so they are all independent one of each other, then we will have limits, bounds for the target that do not make sense. So here the output was normalized installed capacity. So this should be between 0 and 1. But since we were just generating them individually without a dependent structure, then the results did not make sense, the minimum and maximum. when we force the dependence in local features, so if I have my wind speed at 10 meters and wind speed at 100, they are certainly correlated. So if I take these correlations into account that are more realistic, then we see that the minimum and maximum of the output that the can give makes more sense. And if we force, if we generate all this data with correlation between mine and data from the others, then the limits shrink a lot. So to finish, combining data may improve forecast accuracy. Data privacy is a key requirement. Here we propose two privacy-preserving vertical federated learning designs, one fusion-based approach and then a secret sharing-based approach. The interpretability is possible via derivatives, and verifiability here means that we can see the bounds of the output of the model, and future work should focus on developing strategies to do these synthetic data generators that consider correlation between my data and the data from the others, explore alternative CAN architectures. We used B-splines, but we could use other families, test the ability of these models to adaptive learning, and finally integrate with other incentives, because sometimes privacy is not enough. We need, for example, to have some monetary incentive for people to share their data with the others. And that's it. Thank you. Are you there? Yeah. Okay.
Yeah. Let's just see if we have any questions, maybe. Okay.
Yeah, I think we can move.
Maybe
to the
more
last
questions
one.
may appear at last. Okay. So maybe I will step up now. Just share this. Okay. So it should be working. You just get appointed as you were doing also. But okay. So thank you all for being here. My name is Francisco Fernandes. I am also a researcher at INESC TEC. And today I'm going to be talking to you about the work that we have been doing throughout in-field, throughout these two years and some, about the explaining power system dynamics with symbolic AI models. I like to perceive these also as trying to address tasks related to either dynamic security assessment or stability assessment with inherently interpretable models that are generated through AI. So, why is this topic relevant? So if we think about performing dynamic security assessment in the system of today, which is an increasingly more complex system, we have a couple of challenges. The first one is that, in fact, the system tends to be more prone to instability. We have less inertia, we have less short-circuit power, we have a larger number of interacting elements that often interact at different time scales or frequency ranges. And we also have a much larger number of scenarios to be evaluated, often due to the uncertainty of renewable energy sources. This means that for us to be able to say if a certain operating point is secure or insecure, or for us to understand better the stability of an operating point in the system, tends to be more complex. So to be able to diagnose if there is or not a stability problem, a security problem, there's been many tries to use data-driven methods, often based on neural networks, that in fact can do a classification of a system as being secure and insecure, or can pinpoint what is the stability problem that is occurring, but can't really explain it. And also the trust in these models often is low due to its inherent black boxness, let's call it, so they are not transparent. So we see these problems that involve dynamic security and stability as problems where the use of inherently interpretable models like this one are a good fit, because we have a system that the function is complex, and so humans are not very good sometimes at understanding what are the driving phenomena. However, we also want to, after being able to be sure if a system is secure or insecure, what type of problem is happening, we want to be able to inspect our models and understand what are the driving causes of instability. And that's why we think that interpretable models are a key choice here. What are in fact the benefits of these interpretable models for system operators? Well, let's assume that we have a model like this. We will show how we can generate this through AI, but one thing is that they are easily analyzed and understood, because despite them being able to be non-linear, we can keep them at a considered size that it's easily understood for most operators, I would say. Furthermore, they can be further extended with existing domain knowledge, meaning that I can get models like these and try to change them based on my knowledge of the system. I can add new conditions, things like that. They are easily integrated with an existing tool because they are simple mathematics that can be programmed in any programming language. And also, of course, they align well with the current regulatory framework for AI in Europe because they are simple and transparent, inherently interpretable. Okay. So, in what tasks can interpretable models like this be used? For security classification, which is the task where we have to classify an operating point as secure, insecure. For security quantification, which would be to say how secure or how insecure a system operating point is. For preventive control, which would be to say, okay, we have this point that it's insecure, that I have the tag that will appear next. How can I perform an action that avoids this type of problem happening? And also for analysis of local dynamics, which would be to understand what are the main drivers, for instance, for certain types of instability that have local nature, or for understanding what are the main variables that impact the local behavior of an area, of a zone. So to answer this, essentially, we have developed a methodology orientada a symbolic model. I will not go very much in depth into this methodology because I'm going to go through different things, but the paper is also described there. And as you can see, what this allows, let me see, the pointer is visible, I hope. What this allows is that we can get models, symbolic models, or in this case, rule-based models that end up being non-linear because they can relate variables. They can relate variables like these. We can actually include other types of functions like sinus, cosine. Here they are kept generically simple to be easily understood, as this is an illustrative example. But the main idea of the methodology is to pick models like these that a human can write or we can be randomly generated, and the methodology will evolve this through exploration, and it will end up with a model that still is interpretable, but that has a much higher accuracy at performing the task at hand. Okay, so this is the main goal. How is this done effectively? So as I was saying, the starting point would always be to define an initial model, and in this case, define what are the maximum boundaries for this model to grow. For instance, if we have a rule-based model like this, we would have to say, okay, I have a maximum amount of conditions that I want to define that can exist. And I also don't want, for instance, I want the maximum number of operators to be, I don't know, 55 or something like that. So I can still look at the model and understand it quite simply. After that, so the symbolic solver that we developed will get this model. And by interacting with a labeled data set, or with a power system environment, okay, a power system model environment, it will evolve this model into a final version of the model that should be models that can perform security classification, quantification, but that are still inherently interpretable. How does the symbolic solver work, generically speaking? So this is essentially a sequence of different Markov chain processes where we have a solution, we mutate this solution, we test the fitness of this solution in our data or in our environment, and then based on a certain rule that it's not greedy, so we will not always choose the best, we will move on to the other stages of evolution, and we continue like this. So now, based on this, I will show some of the results that we got by applying these to these different tasks, okay? And I will show for some of them the advantages of interpretability. So in terms of the security classification case, so we just need to apply what I have explained before, we just need a label training data set with a set of operating points, saying if the system is secure or insecure. And we will use our method to evolve a symbolic classifier to basically maximize exactly the Defon score. In this case, we end up getting models like this, okay? A simple rule-based classifier that has accuracy from the latest tests that we have that clearly outshine decision trees and even other methods that we have compared, like genetic programming, okay? And we can then pick up models like this and do a validation. The operator can look at them and see, okay, let me see if I can trust these models. So do these relations make sense? Okay, these relations make sense. And second, what can I learn from these? And here it's interesting because on these rules that you can see right here, that they result from using the model in a test bed system corresponding to the Madeira Island power system. You can see that one of the expressions that we got actually introduces basically a penetration limit that conjugates in terms the maximum amount of renewable energy that follow grid code and the one that doesn't in relation to the load. And this was automatically generated, and it makes total sense based on the physicals of the system. Let me see if I can go to the next slide. Okay. Sorry. So this, in the same manner, this exactly the same thing can be done for security quantification instead of security classification. In this case, instead of having a labeled training data set, we would have to have a training data set with the stability score instead of the fact that the system is secure and insecure. And we would train here, instead of using the Defon score, I would use a regression metric, okay? And then I could reach something similar for a regression. What I can also do, because this is a simple rule-based model, is that I can get this model and I can transform it, which is a classifier, and I can transform it into a regressor, okay? I just have to get the values of the equations and transform it, work them in a way that I get an expression. This is actually very well explained in the paper that I showed you earlier. And hence, there are two ways I can actually get a regressor without the necessity of training a regressor. I can just train a classifier and then generate a regressor. And yeah, what this allows is to have something like this, where other than interpretability, I can also clearly see how far each operating point is from the security boundary. This is a comparison of the regressor that has been trained with our methodology and the real value of the stability indicator, okay? And so, as you can see, the patterns are very close. Slide. Okay. Third task, preventive control. So here in the case of preventive control is essentially proposing, in this case, we are considering that the preventive control will be proposing the amount of virtual inertia or synchronous inertia that we have in an island power system. We have a different point of view here in terms of the learning. It's more based on reinforcement learning. I would say offline, because we don't have most of the mathematical aspects based on the reinforcement learning that uses Markov chain theory. And where we have a power system model and we have our agent, and instead of going to a label data set, we have our agent. Our agent takes a decision for the environment provides a reward, and then our symbolic solver will decide what is the next change to do to our agent in order to maximize the reward. We just have to choose a reward in this case. This is a reward that we chose in this case based on not only the stability score, but also on the price that we have for the preventive actions. And once again, we can get simple and interpretable models like this one. This makes total sense, as you can see. In this case, we can clearly see on this expression, this first expression, that we will dispatch much more inertia the less existing synchronous inertia we have. So we will have, it makes total sense, and also it's proportional to the penetration of PV in this case. So the more PV, the more inertia that we will need in terms of preventive control. Yeah, we also did a performance comparison of these with, for instance, neural networks and a human-defined expert system. And in all metrics, the ESMs with the symbolic models outperform the benchmark models. Okay. At last, I would like to talk just about the analysis of local dynamics. So we can essentially tackle the problem similar to what we did for the security quantification of qualification. However, we need to use metrics. We want to do a regression of the metrics that have local nature, okay? The critical clearing time of generators is indeed a good metric for this, but there are many others, like some of them related to voltage stability. So from the point of view of the learning, it will be the same. We will use the methodology with a label training data set. But instead of having here, there seems to be a mismatch. Instead of having the secure or unsecure, we would have a training data set with the different operating points and the corresponding critical clearing time. Okay, and based on that, we could generate different expressions for the critical clearing time. We actually tested these in existing determining the critical clearing time on the simplest systems, which are the one with a single machine infinity bus. So it's just an infinity bus and a synchronous machine or a converter, and we were able to achieve the theoretical expressions that you see here. This can also be done with another approach, which is effectively what one of the researchers that we have in the second open exchange scheme of InField did. Her name is Ika Janai. This was a collaborative work with the University of Manchester and Strathclyde. A paper based on this is coming for PSCC, has been accepted and will be published eventually. And so here, this is a different approach than what we talked about evaluating models earlier. And here, instead of just considering that everything is evolving together, we use a piecewise symbolic regression. Piecewise symbolic regression, effectively, what it does is it will divide the space as a decision tree. And at each leaf of the decision tree, we will have an expression, okay? But the methodology has to choose, okay, what is the correct size of the decision tree that we should have? Should we have a big decision tree and we put a symbolic regression in the middle, in each leaf? Aren't some of the leaves basically the same expression? So the methodology, what it does is it iterates throughout the possible decision trees and aims at choosing a decision tree with minimum size and feeds a symbolic regression in each leaf, okay? Essentially, this is what the methodology does. This is good for systems that are very large, and hence it's important to break the space before providing a symbolic expression. And essentially, this is what it does. And then it also does some types of simplifications and so on. We tested these in this paper that I was talking to you about for PSCC in a version of IEEE 39 with active distribution networks. And effectively, the results were very positive. This is just an example of basically what will be this variable right here is a critical clearing time for one of the partitions of space. So consider this as a partition of space that we have achieved. And once again, this can be very simply analyzed by anyone. There's no complex functions in here. And once again, as was also in other words, as in Carla, and this is also true for the case of evaluation models, after the partitions, all this, we can always find derivatives inside, and we can get either further knowledge from this, or we can actually use, most of the times when we are talking about security quantification or classification, we can use the derivatives to find some type of preventive control when we have problems, okay? And overall, that is it. I'm just letting this to see like how and where could tools like this be integrated to the existing environment of system operators. And I see that in the planning phase, the analysis to analyze the effect of new elements in the system stability security, we can use things like this. train a symbolic model like this and try to understand what is the effect of new elements in the system security, to establish preventive control measures, as it was shown before, and in terms of operational phase, to have, for instance, online dynamic security assessment or reduction of scenarios to be analyzed with time domain simulation. And yeah, that is it by me. Thank you very much. If you have any questions, feel free. Okay, so let me see questions here. Why does the temper increase as a symbolic server is being trained? Okay. Did I stop sharing? I did.
Yes, you did.
Okay. Let me go back. So we are talking. Wait. Here. If I'm correct, is here. So the temperature is a good question. The temperature is actually decreasing here, but I have iterations and temperature, and the first one is the iteration. So the iterations, the temperature is decreasing, and the iterations are increasing. So basically, that's it. This is if we use basic something based on simulated annealing to do the evolution. Now we have shined away a bit from simulated annealing in terms of the accepting rule, but we still keep some of the concepts like the temperature. The temperature should decrease as with time, and based on simulated annealing, of course, there are reasons for it from a theoretical point of view. I don't know if I have any other question, at least. I have a few things. Okay. I don't think I have any other questions. Okay. In regards to the presentation being shared. Okay. Okay, the webinar recording will be made available. Okay, so I think if there is no further questions, we can close here. As Daniela said, the recording will be available. And I think I can speak for everyone here that gave the presentation. We're always free to, when someone reaches out, if someone reaches up to us, to answer further questions or other things. Okay. So that's it. Maybe we'll close here. Okay. Have a good afternoon, everyone. That's it.
Thank you. Bye-bye.
Thank
Goodbye.
you. Thank you.